Hey guys, that was a lot of like me turning my computer around, so sorry for all the noise. We're gonna try this like Mr. Anderson little lecture type thing because I'm not here today. So you should have your chapter 6 reading guide. This is the chapter 6 lecture on metabolism. We will just be doing energy today. So, how do I advance this thing? There we go. Let's talk about energy. What is it? As you probably learned a long time ago in some science class, energy is the ability to do work or the ability to bring about a change. Okay, so that's number one. I will go kind of quickly through this, but if you need to pause me, you can, just like Mr. Anderson. You might even be able to speed me up, but I'm not sure about that. So if we're looking at kinetic energy, that we're talking about energy of motion, right? We're talking about movement. We talked about kinetic energy of water molecules when we did water potential. So in general, we're talking energy of motion. This is number two. Mechanical energy is kind of another way to talk about that. Think about water going over a waterfall. We also have stored energy, which we call potential energy. Okay, we have gravitational potential energy, which I think y'all learned about in physics, where we're above some sort of height and gravity is holding the potential for that energy to occur. In biology, we also talk about chemical energy, that energy that's stored in bonds, which is really important. We had a whole test on that yesterday, which is weird because I'm recording this Monday, but you're watching it Thursday, so I hope that made sense. So the food we eat, those bonds that hold that food together, that's chemical potential energy. Okay, so you're going to move on to number 3 and maybe work through that. So monkey swinging through a tree. Hey guys, monkey swinging through a tree, is that potential or kinetic? Yell it out. Yep, that's right, it's kinetic. That's energy of movement. How about the fig that monkey eats that's hanging from the top of the tree? Yep, the hanging part is what you're looking at. That is gravitational potential energy. How about those molecules of sugar in the fig that monkey is eating? Correct. Again, those bonds that are broken are going to release energy. So that is potential energy. And then finally, that monkey chewing on the fig, there's motion in that monkey's jaw. That's kinetic again. So when we talk about when we talk about energy, we have to talk about these laws of thermodynamics. So this is number 4. Usually I have you guys all like yelling these out, but there is none of you here. My family's not even here right now, so I'm just going to yell. So first law is the law of conservation of energy. You can maybe recite it in your sleep. Energy cannot be created nor destroyed, but it can change forms. So I can eat something, my body can break a bond, releasing energy, causing me to walk around and talk loud. That second law has to do with entropy. Okay, so let's see if I can do this. I haven't used this pen since last year on a snow day. Oh, heck yeah. Entropy is the relative amount of disorder in a system. I can't spell. In a system. Okay, so we're talking about as energy changes forms, it's not a very efficient process. And so that second law states when energy is changed from one form to another, we're losing energy. We're losing energy available to do work, and we're losing it for the most part as heat. Ooh, fancy, fancy. Maybe my video will go viral, hey? So that was 4. That was 5. Number 6 is on your own. Please do number 6 on your own. So let's talk number 7. So free energy. So up until last year, there's an equation that you had to use to calculate Gibbs free energy, change in G. You should know that change in G, delta G, is the abbreviation for it, but we're no longer going to calculate. Okay, we're no longer going to calculate, which is pretty sweet. So free energy is the energy that can do work, and we're talking like cellular conditions, microscopic. That change in Gibbs, that change in free energy is directly related to change in entropy, disorder, and then also heat. Okay, so this should be number 7. Number 8, kind of like we do sometimes, you are going to skip and come back to. Sometimes those fill in the blanks are easier to do in a little bit. But now let's move on to metabolism, because why would we be talking about all of this if it didn't relate to life? So in your body right now, mostly in your cytoplasm, you have thousands, hundreds of thousands, maybe millions of chemical reactions occurring. We've already learned dehydration, synthesis. We've learned hydrolysis. Metabolism is the sum of all of those. Okay? As you learned in chemistry, the things that go into the reaction are the reactants. We also are going to call them substrates when we speak about enzymes. The things that come out are the products. So that should help you with number 10. Now, reactions rarely just have one big step. That doesn't utilize energy the most efficiently. Lots and lots of little steps are sometimes needed to get where we want to go. And so that's what we're going to call a metabolic pathway. That's number 11. You start with one thing, you end with another thing, and then there's some intermediates. Okay, so each step is catalyzed by its own enzyme. So that's what's necessary for each step to proceed. Okay, that should help with number 11. Let's see if this works. Go, baby, go. Yes, yes, yes. Adobe is blocked. Oh my goodness. All right, we're going to skip that. I'll ask Dan about that later. Click on that. I can also show it to you in class when I come back tomorrow. But basically what we have is this starting molecule right here that wants to turn into B, and so you have an enzyme to do that. Then we turn to C, then we turn to D. Well, Simek, why don't we go all the way from A to D? It's not possible. There's not one reaction. There's not one enzyme. So we need all these intermediaries. So like if enzyme 3 would get jacked up, we would never get to the product. If enzyme 1 would get jacked up, we'd never get to the product because we need all of those steps. Beautiful. Let's talk types of reactions. I believe in chemistry you called them like exothermic, endothermic. We have a little bit different ways of saying things, and you got a big fat T-chart to fill out. My advice for this, for the quiz and for the test, is to fill it out in detail. Like this is one you want to fill out well for number 12. So exergonic. Exer sounds like exit, which means out. Energy is going out. Okay, we have a net release of energy. A net release of energy. That's pretty important. The products are going to have less free energy. And what that means is that energy was released. So the products, the things at the end, are going to be able to do less work because we release that energy. So that change in Gibbs, that free energy, is going to be negative in this case. These proceed spontaneously, which will make a little bit more sense when we talk about activation energy. They are catabolic. Woof. What does that mean from chemistry? If you remember, catabolic reactions are those that break down bigger molecules to small molecules. Okay, we're breaking a bigger molecule down to many smaller molecules. We are releasing energy from that. We're probably doing hydrolysis because we learned that before. And our example that we're going to be spending quite a bit of time on is cellular respiration. We have glucose. We're breaking that down. We're releasing energy in the form of ATP. So this kind of shows free energy, Gibbs on the y-axis, the time on the x-axis, reactants to products. We're releasing energy, and so that Gibbs is negative. Everything you just learned is opposite with endergonic. Endo means in. We have energy being put in, so those products have more free energy because we're putting energy in. So requires energy input, putting energy in. That means that free energy change, that Gibbs, is greater than 0. They are non-spontaneous. We're going to keep feeding them with energy. They are anabolic, meaning that we are basically building a bigger molecule from smaller molecules, building blocks. And the one that you should know is photosynthesis. We're taking all these little carbons and hydrogens and oxygens, and we're taking the sunlight energy and we're building this big fat glucose molecule. We're going to be spending a whole lot of time on that reaction too. So you should be able to do number 13 on your own based on the information that we just learned. Let's finish up with number 14 and we're done for the day. Like a 12-minute lecture. That's pretty sweet. All right, let's talk about ATP. We've mentioned it before. It is the energy currency of cells. I have to hiccup, sorry. ATP, adenosine triphosphate is what ATP actually is. And it's these paired molecules that have these 3 phosphates on them, hence triphosphate. It's high energy and it's what we use to generate reactions. It's also pretty hard to store. It's constantly in this cycle being made and then broken down with ADP, which is 2 phosphate groups. You don't have to know a whole lot about this. I'm going to go really fast through it like that. You don't have to know. That you should know. When we break off a phosphate group is when we release that energy from ATP. So I know that you have a picture. Each one of these phosphate circles you're going to have on the left of your diagram in yellow, and then these bigger molecules are kind of your I don't know, there's like a pentose 5-sided one, and then there's kind of a double ring. So what's going to happen is, give me a pen, right here is where hydrolysis breaks off the phosphate group. Okay, so you can kind of figure out where that is on yours. And again, notice it is an exergonic reaction. Okay, it's an exergonic reaction. And so the breaking off and the putting back on of that phosphate is really where the power in terms of energy is. This shows it in a little more detail, which you don't have to know. And that's it. I don't want to go that far. So I think that's it. I hope it was helpful, which is what Mr. Anderson always says. Please be good for the sub. And I'll see you tomorrow. Bye.